Welcome to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn, or manufacturing technology in general, then this is the place for you. I'm your host, Greg Wichman, and with this being our first episode, let me give you a little bit of my professional background. I've been in the industrial automation industry for almost 2 decades. I've had a fun career working with technologies such as programmable controllers, drives, vision systems, and industrial networks. My career has taken me from an end user, where I did system design and programming, to the industrial channel, where I did product management and sales, to here at Yaskawa. In my current role as a segment marketing manager, I work to elevate sales through content and messaging. That also means I get to do fun projects such as this podcast. So this is our very first episode, and it's called Connecting Up. Today we're going to discuss why you would want to connect your VFD to a network. During the show, we'll cover the benefits, requirements, and some of the best practices of network connectivity. And to help have this discussion, I've brought on a guest who is a subject matter expert, Ed Tom.
Hey, Greg, thanks for having me on, and I appreciate being on the inaugural episode for you.
Absolutely.
So real quick, let me give a quick bio on myself for those that may be interested. Unlike you, I've actually been in the industry for more than 20 years, spent the last 19 plus years here at Yaskawa. 7 of them were in the applications group, and then from that point forward, I've been in the product marketing group ever since.
Very cool. Let's kick things off. The episode's on connecting a drive to a network. Ethernet is the network that I'm most familiar with, but if we didn't have a network, what's the traditional way that we would connect to a drive to control it remotely from, not being right in front of the keypad?
Man, you're bringing me back to the days of before I was at Yaskawa in my days in apps. So previous to using any type of a network, whether it be an Ethernet or field bus network, you were looking at your traditional I/O, meaning you're just discrete digital inputs, digital outputs, analog inputs, analog outputs. So a lot of times that meant that if you wanted to get a lot more functionality out of the drive, you were running a lot more wires to it, depending on what that drive was capable of. So if you wanted to just go start, stop, and a speed, great. It was probably about, say, 5 wires. But if you wanted to have the drive stop because of, say, a gate opened up or there was a limit switch hit, now you're running additional wires for that and more and more.
So that can become a lot of copper at the end of the day.
Oh, definitely. And then it became it can get complex not just for the electrician running the wire, but for anyone who was looking at troubleshooting at that point.
Yeah, because your switch may not be on the same panel as the drive. It could be on a panel 50 or 100 feet away. And if you're starting to go into a control system like a PLC, like you said, with all the analog I/O as well as the digital, again, that could be 100 feet of copper that you have to both purchase as well as spend time installing. So what does connecting to a network get us then? How does that get us away from that complexity?
Well, one, I think you hit it. I mean, the complexity of it, because at that point, you're talking about, I kind of mentioned, 5 wires, even for the most simplest. On a field bus or an Ethernet network, you're now down to, and I'll use more Ethernet, you're now down to just your typical Ethernet cable. So there's, I think, 4 pairs of wires inside of there, but it's a familiar type of connection on there. It's what most of us before Wi-Fi used to do with our computers. We would have this RJ45 cable that we plug right into our computer and it would give us our connection. So it's the same kind of concept when it comes to connecting a drive up onto an Ethernet network. You have that familiar Ethernet cable with that RJ45 plug on there that you would plug into the Ethernet connection of a drive.
Awesome. So we're taking a lot of wiring down to one cable. And what can be done over that cable? Are there limitations since it's only one cable, or does it give us expanded capability?
The way I look at it, it gives us so much more capability. Previously, I think I was talking about the discrete I/O and analog. If you wanted to do a lot of monitoring of the system, or you want to get a lot of information, you would be kind of limited on what the unit would be capable of doing. The drive may have, we'll say, 2 or 3 analog outputs, and those would just be the signals that you could read. When it comes to Ethernet connection, it is whatever you want to read out of the drive. If that value or that monitor is available inside the drive, you could pull it over Ethernet. So you weren't limited to what the actual hardware portion of it was. You can read whether it be 2 signals, 10 signals, or if you really wanted to, you could read, we'll say, up to 100 or more signals from the drive.
Awesome. And I do want to dive into the data piece a little bit deeper. But also, I think it brings with some new topologies for connecting as well. We talked about all the copper required for one drive, but if you had 2 or 3 or 5 drives and you had to run, let's say, to that panel 50 feet away, every single one of those needed the 5 to 10 or more copper connections. Does Ethernet bring a new way to connect drives together, where do I have to run 5 Ethernet cables, one for every drive?
That all depends on how you want to do your system. In some instances, that separate Ethernet cable for every single drive, that's definitely one of the methods. You can definitely do that. Most people will call it like a home run type of installation. You bring it back to a common panel.
Or a star topology. Every drive has one cable that goes back to its own port on a switch.
Exactly. Star tree topology. But some of the other things too with what some of the connections that are available out there is that some Ethernet connections on there, or some, we'll say some of the Ethernet options that are out there may provide you a 2-port type option on the drive. So instead of doing a star topology that we were just talking about, you could potentially daisy chain from one unit to another. So using that same example, 5 drives and it's 50 feet away, you may run one 50-foot Ethernet cable to one unit, and then you would jump from the second port of that to the next drive, and then on, and you would just do that for all 5 drives. Now, the step up is for those that might think, well, what happens if something were to happen to the network? You could additionally run one more cable. So you'll have now 2 cables coming from that main panel running 50 feet, one to the first physical drive and then one to the last drive physically connected, and have what's called a ring network. And what that provides now is some redundancy so that if, say, a unit was powered down for some reason or another in the middle of that, you're still able to communicate with the remaining drives without any issues.
Awesome. Yeah, I've heard that referred to as a device level ring before. And one nice thing is you can lose any one cable segment in that DLR for short, and the network still stays up and communicates. Or if you do have a process where maybe not all 5 drives are required, to your point, you can take one offline and all the rest remain communicating and operating, whereas in the linear topology, you would lose anything beyond the drive that you took down. All right, so not only are we down from multiple copper wires to one cable, but we have new topologies that allow us to eliminate even more installation costs and time. Now let's go back to the data collection piece that we started to touch on earlier. You mentioned that when a drive is on a network, we have access to all of the parameter information from set points to active running values. What are some of the most common pieces of data that people like to monitor, and what benefit would they get from doing so?
Some of the ones that I can recall that most people will monitor, one is usually their output speed or output frequency. Most people are always wanting to know how fast it's going. The other common one is your run status, see if the unit is running, not running. And lastly, I want to say the last one that most people will pull out is going to be your fault status. You need to know whether or not, hey, if it's not running, why is it not running type of thing. Beyond that, I think some of the ones that are coming to mind right now is output current, and really want to know how much current is being pulled. Are you overloading the motor, or is there something about your system that is driving a higher load? So that way they can watch the output current and see where things stand when it comes to a benchmark that they may have created.
As we're pulling this data, 2 things come to mind that you would do with it. And one is it gives you the opportunity to live monitor the data. When we're talking going into a control system, oftentimes there is a human machine interface or an HMI somewhere on the system. So the cool thing is all of this data that Ed's talking about that you can pull out can be viewed real time, whether you're in the HMI or if you are a PLC programmer, you can actually go into your control system and see all of this live. I think one of the other cool things is because we're not always in front of the machine, the system, the process. We can't, as a human, monitor them 24/7, but computers have ways. We have data logs, we have historians, we have ways that we can be continuously capturing this data so that if we're not there when that fault occurs, we can go back and historically trend all of that data to figure out what might have happened. And I like that you brought up the output current because you might trend 30 minutes before the fault and see that your output current was continuously rising at a steady rate, meaning the motor was working, the drive was working harder than it should have been. Maybe something was mechanically seizing or breaking down in the system. So it can help you with that root cause analysis of why your system might have gone down. That's historical, and we all like to figure out why a problem happened so it doesn't happen again. But are there ways to use this data to start with all the computing power we have now and the buzzwords out there like AI, machine learning, and predictive maintenance? Are there ways that we can actually look forward with this data to see what the process might do in the future?
Definitely. I mean, and I'm going to rewind a little bit and I'll hit up your predictive maintenance and looking forward as well. But also, and actually, now I think about it, it's going to be a little bit of a twist to it, is that with all the data that you're pulling into or capable of pulling into your controller, you can now take that and not only say use it for a predictive or preventive maintenance type of scenario, but you could also take it and maybe even see how you can even use that data for your application itself. How can you refine it and tweak it? So whether it be, I mentioned, I used output current earlier as one of the example, but how can we monitor the output current and know how to adjust the application or adjust your process so that it gives you the yield that you're looking for? So there's just so much you can do just even, I'll say real time and by having that set into your controller, but also on the predictive and preventive maintenance portion of it, you could look at stuff like the DC bus voltage and monitor that and kind of go, well, I see some of these trends are starting to occur. And then based off of those trends, be able to sort out that there could be something wrong with the machine. Maybe something is wearing on there. You mentioned seizing up. Maybe the current is now starting to go and there's a bearing that's seizing up. Or there's maybe a seal that's starting to go and that might be a reason why we're watching the current jump up and spike up suddenly and come back down again. So many different things that can be done just based off of the data that's being collected.
Yeah, and I'm going to elaborate a little bit on predictive maintenance because I think it is a really cool topic. Almost all equipment has some type of a preventative maintenance or PM schedule. And historically, I think they're very time-based. Like we're going to replace this gearbox every 12 months because it's based on a manufacturer's recommendation or maybe something you've learned over the years of when it tends to fail. But one of two things can happen with that. One, if it fails early on you in, say, 11 months, it could lead to a catastrophic failure and break a lot of other parts on your equipment. On the flip side, which you'll unfortunately never know, is that maybe that gearbox would have lasted 16 months and you just essentially wasted 4 months of cost of a gearbox. So the whole idea of predictive maintenance is to monitor all this data in the system to actually know when these parts are getting close to failure by monitoring things like vibration. Is it normal? Is it increasing? Is it changing? The current, is it normal? Is it increasing? Is it changing? And I think that's a cool thing to say, hey, we're at that 12-month point, but everything's running A-okay. We're just going to keep monitoring. And then at month 13, all right, now we're starting to see some symptoms. It's time to actually make that change.
No, I agree. It's nice to be able to look at all of that and know exactly where you stand before you put in some of the efforts. It could be the difference between scheduling maintenance for, say, 2 weeks out or 3 weeks out versus, hey, you know what, from what we see right now, we could probably push this maintenance out to about another 2 or 3 more months and keep production going. And I think we can agree that if your production's running, everyone's happy at that moment.
Absolutely. And when you're saving that OpEx or CapEx, there's even more people happy. Since we're talking about cost savings, another big topic is energy consumption. And with the ability to monitor data from your drive is the ability to monitor energy utilization and quality. This can bring a couple of benefits. One I can think of is to make sure that your process is running as efficiently as possible. That helps keep utility bills low and reduces the energy footprint on the environment. Another benefit of monitoring energy is the ability to do further root cause analysis. For example, you could be chasing down a troublesome recurring fault, and you've looked everywhere in your process, but you can't find the culprit. But now, because you're monitoring the power coming into your drive and logging variables such as the DC bus ripple, you can actually determine when a problem might be due to something external to the process, such as the incoming power from the utility.
Yeah, I mean, when it comes to energy monitoring, whether it be for energy savings, whether it be just trying to see what's going on, I got to admit that the drive can act as kind of a different sensor. I mean, you brought up a good one with the DC bus voltage. Some people may go, hey, my voltage coming in is 480. I know it's 480, and that's what it's supposed to be. But yet, if you were to monitor the DC bus voltage, you may see that spike up all of a sudden, and that would help indicate, no, something is going on with your main lines. So it's nice where there is just all that different bits of information that's available out there for people to use.
Because most of those issues we have don't last very long. Every time we put a meter on, we might see 480 volts. But again, it goes down to that difference of I can't be in front of my process 24/7, but when I can start recording the data from it, I can look backwards, I can look forwards, and I can start to make my life a little bit easier.
Oh my gosh, you put up such a good point on that one because yes, we can never be there all the time. And this definitely helps to have something that's available to you pretty much as long as that unit is powered up and your PLC is running, you have something that can give you that information.
So maybe that's a good segue because we all love those problems that somebody claims are there, yet every time we look, they're gone, those ghost type problems. So let's talk about a few good practices or best practices to make sure we don't have those types of issues with our network. If we're wanting to put our VFD onto a network, and we'll stick with the Ethernet theme here, what's the requirement and what are some of the best practices that you know of?
Some of the best practices, one I'll hit on is definitely the separation of your low voltage and high voltage. Some people may look at it and go, well, it's easier for me to throw my Ethernet cable with my main power lines because I've got the conduit.
Oh, big no-no.
Oh, yeah. Definitely don't recommend that, no matter what kind of shielding you put into the cable. So always look at wanting to put that separation in there. One that people will also say is if you have to get close or cross high power lines, you say do it at a 90-degree angle. And it has to do more with just the way the electrical fields are generated and noise that can get into the cable. In an industrial environment, I highly recommend the use of a shielded cable. We were just talking about the high voltage, its proximity to that. You definitely want to consider using that because without it, you can have just the introduction of more noise into it. So as someone had put it one time to me, if you get noise into the cable, it could delay a message from getting from point A to point B.
Yeah, absolutely. And the way most networks operate is if they can't interpret the signal coming in when they do their checksum on the data, they will basically, depending on the type of network, they'll either re-request it or they'll just drop it and wait for it to come in again. And based on oftentimes your RPI settings, how fast the system expects that data to come in, if it doesn't see it after so many milliseconds or after so many dropped packets, it will actually fault out the entire system. So that's where we want to be very careful that we're not introducing that noise. That's why it can act like a ghost. I've been in front of a rather large piece of machinery. It was a multi-cell welding station. And it might have been because they were in their commissioning phase, but all the networks would come up and check out. And as soon as they would start the cell up, things would start to get flaky. Sometimes it would run great, sometimes it would shut down. Went and looked inside the first panel and I saw Ethernet cables draped in front of VFDs. So when you think about it, when the machine is down, those VFDs are not active. then the Ethernet network is working fine. But when the drives would spin up and start to create a little bit of EMF, a little bit of noise, it would get introduced into those cables. Sometimes it might run 5 minutes without a fault. Sometimes it would fault every 5 seconds. So when I talk about these ghost-like problems, I don't want to scare you away from Ethernet or the technology, but there are these best practices we highly recommend that you follow.
To kind of stress on that point, though, even though we're talking about the ghosts in the system when it comes to Ethernet, the same could actually hold true when it comes to discrete as well. To try to pin some of this on Ethernet at times is probably understandable, but at the same time, if someone were to drape, say, an analog signal or analog cable in front of that VFD, all of a sudden your speed starts jumping up and down and up and down. You're wondering why. So I just wanted to clarify, people always kind of go ghost in the system for Ethernet. Oh, I've seen that even with our good old-fashioned IO.
And this is a great point. I probably give it too bad of a name in that regard of the realm, but is really best electrical practice for any time we're talking more than just a digital on-off type signal. So obviously we've hit the cable, we've hit the topologies a little bit, but real simple is our VFD needs a COM port on it too, right? And some of those are embedded, but we also offer COM cards that can be added to any drive, whether it's already a drive in an application or it's a new application.
Yeah, we definitely have the option to be able to both put in an option card where you can have either one Ethernet port. So if you want to do that, the star topology we were mentioning earlier, or we do have ones with 2 ports on them. So we were talking about that line or ring type of topology. You have that option.
Is there anywhere else on our drive that someone might confuse the port to be an Ethernet port?
Oh my gosh, you're bringing up the RJ45 port that we use for the keypad. And yeah, that is one area that I would recommend to never plug your Ethernet cable into and then plug it into your computer. That is a serial port, and I have heard too many horror stories of people taking out their network card on their laptop.
So I brought that up on purpose. If you do a remote connection for a Yaskawa keypad, so you're removing it from being directly on the drive, we do use an RJ45 connector. But as Ed said, it's serial, and if I understand it right, the drive sends a voltage to the keypad to power it up. And if you plug that into something like your computer Ethernet port, it doesn't like that voltage. And that's where those issues arise. Once you're physically connected to the network, is there a lot of setup that needs to be done within the drive itself?
I would say your typical network settings. So like everything, we do need to be able to address or know where to receive the messages from. So kind of think of it like a home address, except we'll call it the IP address and network settings. That is one of the things that will need to get programmed in there. But by default, the drives will try to get an address from whatever the network controller is. Best example is a DHCP server. So it can actually get an address from there. So if that's what you prefer, it can definitely do that. But I've seen a lot of installations where people prefer just to put a static IP address and network settings into the drive so that they know exactly where they're communicating to and where they're getting or where they're sending their messages to.
I can see exactly why that's important, because now we need to talk about the other end. So we have our network physically installed, we have it connected, and we have that IP address or node or home address set up for the drive. The problem with DHCP is every time you power down or reconnect, you can get a different address. And if we follow the cable to the other end, we're probably plugging into a PLC or some type of SCADA control system. And that control system always wants to know where that drive is. If that IP address changes for any reason, that's going to break that communication channel. And that's why usually in industrial settings, we see a lot of static IP used. But continuing down that avenue, what needs to be done on the PLC or control system end to get all of this wonderful data we have available from our drive?
That portion will depend because there's just so many different flavors of Ethernet that's available out there, whether you're on the industrial side or on the commercial side. That'll depend on what controller you've got on there. But what I will simplify it to is that your most basic thing is getting the drive connected up there. It's typically a simple process. Depending on the controller that you have out there, you can spend probably about a minute, maybe less, to get a unit up, running, communicating with the controller. And then after that, it's just going in and picking out what data that you want to communicate with. And typically, I mean, myself, I know I've done it many times, I can get it communicating in that minute or less. For those that have done it for the first time, they'll be meticulous, go through the instructions. And I've seen some people where, depending on which network,
Might take you 2 minutes then, right?
Yeah, like 2 or 3 minutes. No, I mean, I know you're kind of joking, but actually I have seen people do it in about 2-3 minutes. And then afterwards they go, well, what if I wanted to add some more, and just be able to just knock out multiple ones really quickly. So it is surprising that there's that kind of hesitation at first because you're not sure, but you'll say, like, when you connected your computer onto a network for the first time, you're like, okay, how's this going to go? And I'm dating myself back to dial-up. So when you go into dial-up and you call that one server, you're like, let's see how this goes. There's always that
connecting to AOL to see if you've got mail, right? I can date myself as well, but I'm very familiar with those dial-up modem sounds and the happy message when you're like, yes, I'm on the internet. Another thing, when I go back to my early days of networking, what kind of always scared me or confused me was this whole idea of memory registers. When this data gets into, let's say, a PLC, is it going to be a bunch of cryptic registers and I have to figure out what I'm looking at, or is it easier than that?
It has gotten a lot easier than that. And I know what you're talking about. Back when a lot of the field buses and when Ethernet was first released, it was a little bit of the function of just the controller at that time. You would have these cryptic messages of, it is at this, we'll say, N269, and you're going, what is N269 at this moment? But no, there's a lot of tools and a lot of improvements on the controllers and the programming that help make it so that there's better tags out there. And again, regardless of the whether or not it's an industrial or a commercial protocol, we have those tools available so that you're not trying to figure out, which one is my run command? And then just page through and just maybe even try turning on one bit at a time and going, drive's finally running. So it's been heavily, I would say, heavily, I want to use the word simplify. I don't know if that's the right word, but it's definitely eased it up a lot.
Yeah, I remember not having documentation. You'd change a speed and hope that you can see which data tag is moving. A lot of control systems, PLCs now, are exactly that, tag-based. And we have pre-engineered code that can drop into some PLCs and basically map all that data out so that if you're looking for output current, there is a tag that says output current. If you are looking for speed, if you are looking for start stop. So it's plain English now. That's what's been simplified instead of those random registers. Sometimes even in different bases like octal or hexadecimal, all the different ways that we used to have to read memory architectures. So yes, I think simplified is a great word for how things are today. Aside from a few best practices to pay attention to, seems like networking your drive is pretty straightforward and brings with it many advantages. I still see a lot of implementations, though, using the hardwire method for control. I wonder if there are still people with hesitation, not because of the setup and programming, but because of security concerns. I still know a lot of people that refuse to touch any tools that are cloud related for fear of someone stealing data or overtaking machine control. While there are real risks, I know that just like with best wiring practices, there are best practices for network security. Do you have any insight you can share on that topic?
Boy, this one, I'll try not to get into too much of a.
This could be 10 more podcasts, by the way. This could be a huge subject, but
it can be.
We just kind of want to skin the top.
But there's always a lot of different ways to do it. I think if you were to go out there, look at different network practices, there's one that I would say one of the terms that had come up a good amount was called defense in depth. And ultimately, that one just summarizes to think of it back at the days of the medieval castle. You had your moat, you had your gate, you had your guards, you had a whole bunch of different things, but they were all just different layers to help protect everything that was on the inside of it. And that's the idea with defense in depth, is having the external equipment available.
It's not just the equipment, though. It's also the management of the equipment. I'll jump into a prime example, as I've seen people that put a firewall on a network. If you don't know what a firewall is, it's a security appliance to monitor and control traffic on your network. And they think they're secure. And to your analogy, that's, well, maybe I have the moat, but if they have a boat, they get across, I have no gate, I have no guards, I don't have anything else. So it's one piece, or it's not configured properly. They maybe do an auto setup out of the box, but it hasn't really been finely tuned for their network. Now, firewalls are typically only needed in a pretty elaborate network design. When we're just talking a machine network, you're not usually going to have a firewall on it. But I just want to point out that you need to manage the things you run in your network. For example, password management is really important. Computers on the network need to be password protected, especially those that have access to the PLC or control system code. The most obvious reason this is important is to protect intellectual property. But often we're simply trying to prevent changes being made by those who aren't authorized to do so. Those changes could be purposefully malicious, but more often than not, it's someone trying to help. Maybe they are troubleshooting a problem and make a change to code they don't understand, or just accidentally click somewhere they're not supposed to. In this case, the action is meant to be benevolent, but lacking these layers of security could lead to a change that is catastrophic for a batch of product or for the equipment producing it.
Yeah, you have a good point on that one. I don't know what the percentage is, but they've went out, looked at it, and they go, well, the number of times that someone created any problems on a network, it wasn't out of just malfeasance. It was just they had the access to it, and they probably shouldn't have, and they accidentally changed something that they didn't have to, and then it could have been an hour, couple hours, day of downtime because of that. The access control portion, you're right, is probably really big for those that are putting together a network and maintaining that.
Excellent insights. We've touched on a lot of topics today at a very high level, but I'm hoping our listeners have been able to pick up some of the key benefits of networking a VFD and some of the best practices to do it right. Ed, any closing words on today's topic?
I mean, nice thing about networking a drive, or whether you're using Ethernet or something else, I think we mentioned earlier, is that it's not as scary as one thinks. It may seem a little bit, for some, daunting, because you're getting the bits and bytes flowing through a cable versus being able to measure the signals coming in. But really, I would say it's no different. It's just your tools have changed a little bit at that point. And it's proliferating. It's definitely a lot more out there, but it also offers such a large gain from what you can possibly do. For those that have the imagination and go, hey, what can I do with this? If I read this information, what else can I accomplish with it? It's there. The information can be there and can be used in whatever application you might be using, or whatever coordination of a system that you might be doing, whether it be a machine or a building. I think it's going to be something that we're going to see more and more of. We definitely see it in our everyday lives a lot, but we're definitely going to see it a lot in the industrial world as well. And we're going to continue to keep evolving with it.
Very true words, Ed. I appreciate your time today. Thank you for joining us and sharing your expertise.
Thanks, Greg.
If you want to learn more about this topic, make sure to reach out to your Yaskawa regional drive specialist or local Yaskawa distributor. Please like or follow this podcast to stay informed when new episodes launch. And if we're doing a great job, leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.